Yes, on the moment to start, I would like to welcome you all here in this public lecture given by Dr. Huang, that he pronounced it very well. This is organized by the International Computer Chess Association, the University of Leiden, and then it's the dependents of LIAX and LCDS. And if you look at the program for the events we have, there are many more sponsors. I refrain to mention them. My name is Jaap van der Herik. I will be succeeded by Hideki Kato, and then we have the main speaker. And finally, the meeting will be completed by Professor Aske Plaat. That is for this afternoon. I will take 2 minutes. Hideki will take 5 minutes, and then I will have to say one more thing. Apart from the lecture, there is also a question and answering compartment. So during the lecture, you can prepare your question. I'm here to honor Huang, and I do so on behalf of the ICGA. The ICGA stands for the International Computer Games Association. From the beginning, they have a best performance award, a best performance in the publication, either table basis or whatever. And first it was called the Mephisto Award, then the Nova Award, then the Chess Base Award, and finally it is now the ICGA Award. Not to, I would say, to interchange with the ICGA Publication Award, that's a completely other thing. So it is for the best performance in the year 2015. And it is without any doubt, as you may understand, that the jury decided to award this to the Google team DeepMind for the performance, not in March this year, because that's 2016, not for the publication in Nature, because it was in January 2016, but for the performance in October 2015 by defeating the European champion by 5-0. I would like to ask you to come forward and then to take the award, which I show you here. Oh, what's this? Okay, anyway, this is the award. Yes, okay. Having done my job in this case, yes, we have a second award. The second award will be handed over by Hideki Kato. He is a representative of the team Deep Zen, a previous contender of AlphaGo, and he is also, because he did so on behalf of the Computer Go Forum, and he is a board member of the Computer Go Forum. It is my pleasure to give the floor to you.
Firstly, I'd like to introduce some about our award. Our HuangTago Forum is a non-profitable organization in Japan. And this award has the history of 20 years. The first is given to Thomas Wolff in 1996. The awarded persons include David Fortran, Eric van der Wal, Mobati, Red Coulomb, 2 years ago, the late Don Daly, and Nick Weddle last year. This year, we HuangTago Forum proudly declare our annual award 2016 is given to the Google DeepMind team for the development of AlphaGo and the first ever win against top level professional Go player, Ike Sedo. Okay, picture.
Yes.
As a part of our award, we our forum gave some memorial to whatever awarded person. Last year, for example, I sent a large map of Japan in English version to Nick Webb. His favorite is collecting maps. This is what relatively is. But for this year, the team's achievement was so great. So it's very difficult to choose memorial. But luckily, very fortunately, there are almost the same level of things happening in Japan. Yuta Iyama first even possesses a 50-year crown of Japanese Go title, 50-year. He possesses all 7 titles in Japanese Go War. Yeah, very great. So I chose Memorial Fund for this is fun. The left side is signature and battle. Also, there's 7 titles here. The center are idiom of 200 characters. It's read from right to left according to all the Japanese rules. Ko tats. Ko is wide, tat is too rich. This idiom means with broad mind to reach the deep of the truth of things. With broad mind to reach the deep of the truth of things. I think very good for the team. But unfortunately, due to the limited budget of our forum, I will prepare after only 2 months. I know the 3 key persons of the team, Demis Hassabis, David Silver, and Aja, all play for. Yeah. So these are 2 from the forum to Demis Hassabis and David Silver. And I prepared personally one for my best friend.
Thank you.
From me. Thank
you very much.
There is still a thing, I forgot one thing, and that's in between, but I do it now together. It is, I would say, polite to give Aja Huang the floor to thank for both presents, as you understand. That is at least in Japan habit. So, but I will not interfere twice. So I announced that he started with thanking for the 2 awards, and then he immediately starts thereafter his talk. And his talk, you will see the title, but I give you another title, and that title should be From Erika to AlphaGo. Erika is the program with which he started to be well known in our world, in our ICCA ICCA events world. So he was always a front runner in Go. I could tell many things about it, but I will leave it to him. Aja, it is my pleasure to have you here. I may say I'm very, very happy and indebted to you, and we are proud of you as a member of our community. Okay.
Ladies and gentlemen, I'm very happy to be here. I'm Aja Huang from Google DeepMind, from AlphaGo team. Thanks very much for the award. I'm really honored to be here. So today I'm going to talk about AlphaGo. The topic is combining deep neural networks with research. So the first slide is this one. I know many of you must see, maybe you watched the match, enjoy the match. It was a very happy moment for me when I see AlphaGo receive the honorary 9P, which means professional 9-Dan certificate. from the Korean Bad Association, Go Association. Yeah. So it has been a long time dream of us that we can build a strong Go program. So actually, I have been in this community for many years. Actually, so I will talk about my history now of ICGA. So it was in 2006. I still remember it's in Turin. The city doesn't have many restaurants, I still remember. And I entered my first Go program, AlphaGo. So Aja is my name, because my Chinese name, Huang, Ajie, so I call Aja. So I entered the program for fun, actually. Why I say it's for fun? This is how AlphaGo works. I will describe now, very easy. If AlphaGo is black, you will play at the center for the first move, and then start mirror, whatever white player start mirror. If the mirror point is illegal, you will play a random move until the end of the game. If AlphaGo is white, if the opponent play at the center, you will pass. Then start miracle. So the program was actually a few hundred lines of code, you know. So when I described the algorithm to Professor Yicheng Wu, the creator of Connect 6, so he told me, Aja, you're here for fun. Just for fun, right? I told him, yes, I'm here for fun. So that's the first year I entered my first Go program, AlphaGo. I had some photos, but it has some problem here. So I will just describe. At that time, I see the photos like including Ryan, including like Professor Herrick, many people, like including Remy Collin. So it was the first year he entered the first in the history, the first Monte Carlo tree search program. Yeah. So I still remember, because at that time I'm trying to learn from the community. I'm a PhD student, and from Taiwan. My English was a bit broken, you know. So I try to speak to people as more as possible, to try to learn from them, try to communicate from them, with them, and try to how to say, experience the fun, yeah, of the tournament. I still remember Remy Collin was staring at the screen all the time. Yeah. So he won the 9x9 competition that year. So that proved, actually start the whole MCTS area that still dominate. Actually, AlphaGo is using MCTS. So Remy was staring at the screen, and I tried to speak to him, but I think he was amazed that, because he is not so strong, he was amazed that his program can be so strong. Yeah. So that's 2006. In 2007, I still remember the Computer Olympia was in Amsterdam. Yeah, I entered, so we play computer chess program that year. And so AlphaGo was a bit, broken, so I didn't continue. And so that year, Mogul entered the tournament, Mogul. So that was the year that really motivated me to get in computer Go area. Why? Mogul's author, two main authors, is Huang, and the main author is Liam Galley, Savant Galley. And he is a Go beginner, He doesn't know Go very much. So he just keep asking me, who is the head, Aja? Who is the head? I was very impressed, He is the author of the strongest program in the world at that time. But he is a Go beginner. So you know how strong is the powerful MCTS plus UCT. Yeah. So many people have maybe read about the paper of UCT. That's a revolutionary paper. Yeah. So I was really impressed because I played against Mogul there, 9x9. At that time, I didn't believe that he can beat me. I didn't believe. I thought no program can beat me on 9x9 Go. But Mogul beat me several games, and Chris Stone too. So every time we said, oh, okay, start again, just play. I played very hard and lost some games. So at that time, I really motivated to start computer Go research. So I say this is, I want to say that I grew up here. That's why I'm really honored to be here. Yeah. I was compete. I would, learn a lot from here, and actually many good ideas are spawned from this community, including Monte Carlo tree search, many machine learning, and many, game-related ideas. Yeah. So. So my laptop will go to sleep 5 minutes, every 5 minutes. It's not changeable. It's a Google machine, so it's preventing that you forgot. Yeah. Okay. So maybe I have to do something every 5 minutes. Yeah. So when I do computer Go, why? So you can know that because I like Go. When I started in 2007, when I played against Mogo and Greystone, I was intrigued because I like Go so much. So I want to build a strong Go program. So it's a fun for me. It really, because I like Go. If I wrote a program that can be very strong, I will be very happy. I think that's the same with many people too. They write game programs because they like the game. And we like games, right? No matter video game or board games. Because games are so fascinating to us. And when I joined Google DeepMind, I found another aspect of game programming. Yeah. That is, game is the good aspect of artificial intelligence. Yeah. So Google DeepMind, when I joined Google DeepMind, I realized one thing, that is that for fun, actually there is another good motive for the game development. That is this AI. Yeah. Because game is, is very, very concrete objective. Right? You have win or lose a game. There are concrete steps. There are different types of games. Some are complete information. Some are not complete information. Right? So DeepMind's mission is to solve intelligence and solve everything else. Yeah. And use it to make the world a better place. So we do AlphaGo, except that I like Go from my perspective. But DeepMind do AlphaGo also is to promote artificial intelligence. If you say that if we can solve Go, it's so complicated, it's an enormous search space game, then we can handle many problems because in the real world problem, there are so many possibilities. We can make the range smaller to that we can handle, that trackable. You know, if we do brute force search in Go, it's impossible, right? So we can make the problem trackable. Oh, really sorry, 5 minutes. So now I will talk about AlphaGo. So I personally operate AlphaGo against Leiden and Huang. Every game against pros. I was very honored because in the past, I think many people, even professional players, told me that in their whole life, they have no chance to even sit in front of Leiden to play one game. So he, like my friend was told, I have a pro friend, he told me that, actually, I'm proud of you, you know. But I was very honored too. Yeah. So I tried to respect him during the whole match, although we didn't speak. Yeah. So yeah, he didn't speak English, but we speak at the board. Yeah. So what is the key of AlphaGo? Why AlphaGo can reach such a strong point? You know, when I do computer Go in 2010, I have a program, Erica. I spent a lot of time to do handcrafted features, large patterns, improve the playouts, you know, and all the time I spend small change, see winning rate, and see which feature help. Of course, I do machine learning too because I train the features by some method, you know, machine learning method. But at that time it was very long way to go to achieve professional level, even the top professional level. Yeah. So why AlphaGo can be so strong? What makes AlphaGo so powerful? You know, there's a big jump in playing strength from Erica, or the strongest program that well-known Zen and Greystone. It's from 6-time amateur to professional. There's a 3 stone gap at least. Then there's a big gap from the weak professional player to the top professional player. Why AlphaGo can jump so fast? When we start AlphaGo, we make a decision that we don't do the old ways. If we do the old approaches, we become a bit stronger. There's meaningless to us. So we start a new approach. We try to do deep learning from this deep learning side to see whether it works at all. Yeah. So the real power of AlphaGo comes from the deep neural networks. That's what I want to focus today. That it's really powerful. I'm in the experience of this. In the beginning, I didn't believe it. In the beginning, I was really impressed by the power of neural networks. I still remember the first time I tried the Palace network. That's in the end of 2014. So at that time I was thinking, maybe I rebuild something from Erica, right? I have experience. I can rewrite the code and the features. So then we tried, okay, then let's try PowerSnet. What about we just do a network, learn the professional moves, and then we plug the network into the MCTS, see what happened. I still remember the first experiment. That's, I never forget. I see the win rate is 100% stronger. It didn't win, it didn't lose any game in the whole many games. It's like 100%. So we said at that time, it's immeasurably stronger than the old approach. Yeah. So I was very impressed. That's the start of AlphaGo. So we published the paper. The paper name is Move Evaluation by Deep Convolutional Neural Networks. Yeah. If you are interested, it's mainly developed by our intern, Chris Madison. It was very interesting work. Yeah. Our adventure start the goal with deep learning. So if you see here, I want to show you. This is a chess game, right? So I want to confirm that chess haven't reached the best player, right? Haven't. Maybe is right. Is that correct? Haven't reached. It's still far from. Yeah. So AlphaGo is still not yet. Yeah. So you see the chess is the search space is very huge. But Go is even bigger. It's enormous. So it's impossible to do brute force search. Now, the real power of AlphaGo is in convolutional networks. That we use two types of neural networks. Even today, the basic power of AlphaGo lies in these two networks. The first one is the value network that we use in MCTS to evaluate position. So we know, I just say that Remy Holland started the revolution of Monte search. It's by what? It has a tree search. Every time you reach a lead node to evaluate a goal position. It's because it's very hard to come up with a static value evaluation function, right? So we do a multicolor rollouts, and when the rollouts gets more and more, the average value gets close to the good value. It is the proximate value. So value network replaced that. Actually, he actually evaluate directly, provide a value function. So I know many people think that it's very hard to come up with the evaluate function, right? But that's actually what humans do. When we play Go, when we see a board, we say who is ahead on the board. We basically just stare at the board. Then we look at every region of the board, right? Then we say, okay, maybe black is ahead. We maybe count the territory. Then we conclude that, oh, in this position, black is ahead. We don't do wrong, actually. This is from the human perspective. We just look at the static board. This is what the neural network do, the value network do. You basically make a static evaluation of the current board. The other one is the PowerSnet network. I just said that's immeasurably stronger. In the beginning of the development of AlphaGo, I was really impressed. And this is just you take a board representation, and then it output a probability distribution of the current board. He says which moves are more promising. You have a distribution. Then you search accordingly, use this distribution to do search. So these two things, the PowerSnet network and the value network, are the key of AlphaGo strength. So here we have this research. So value network basically reducing the depth of search, because he can stop on any node. He doesn't need to go all the way to the end of the game. Then he can return the value of the position. And PowerSnet network reduce the breadth of the search, because he doesn't need to search all moves. He can, like a Bing search, he can limit the search onto some promising move, maybe 20, 10. In some position, maybe there's just one promising move, so as to make this whole search, big search, to a tractable condition. Now I will speak about how to train these neural networks. This is very important, because the neural networks they are so complicated. They are very powerful, but they also need very long time, very careful training, and it needs much resource to train. Yeah. Okay, so basically, at first, how do we train the policy network? We basically take the human games, many expert games. We treat them, okay, now we just want to mimic those strong humans. So we do supervised learning over from the human games. So we have the policy network. Then we use reinforcement learning to do self-play. We basically play the policy network against itself to improve itself. Then we have another network, which is called the RL network, reinforcement learning network. Then we use the RL network to do self-play, to generate self-play games. So this here is self-play data. Use this data, we train the battle network. So you can see that actually AlphaGo's real magic lies in battle network, and it's actually several steps because you have to train. You need a policy network first. You need to improve the policy network itself to become strong in self-play. Then you need to generate the games so that you can do regression on this game, on these outcomes. And then you have after all this, you can train a battle network. Okay, so this is the policy network. So we use many details can be found in the paper. I want to say is this. So we try many different architecture. What we write in the paper is the one we found is the most effective one. So why is 12 layer? Why is the filter is only 196? Why not more? Because we found this is the most effective. So the policy network actually just have 12 layers, and the training data is here. Training algorithm, basically it just to maximum likelihood. And you can see that it takes 4 weeks on 50 GPUs using Google resource. So I would say AlphaGo's success won't be possible if we are not in Google. Yeah, because we use really a lot of resource to speed up the training. And Google has really good framework. Yeah, we are really grateful for that. So AlphaGo is many things together is make it possible. Yeah. Okay, so it reaches 57% accuracy on KGS dataset. We use KGS games. Then we do reinforcement learning. Basically, we play a different policy network. So many people say that AlphaGo can play against itself to learn from itself. So they feel this is really amazing because human they improve slowly, right? And AlphaGo can play against itself too. This is the power of reinforcement learning. In the past, actually, I don't. In the past, I don't really get involved too much in reinforcement learning because I thought it's not useful. But in AlphaGo, I see the power. This is really powerful. So if you play different policy network, you can just use reinforced policy gradient to make the network stronger and stronger. And then you get a network that's really strong in play games. Okay, so it takes 1 week on 50 GPU using Google Cloud to train the network. So the network itself, if you play the game, it reaches 3 amateur then. So I can tell you one story. One day, I was checking the experiment, ILMET. This is what we call ILMET because it is trained by reinforcement learning. So we have a terminal system, right? So we have Keystone there, the strongest version of Keystone. So the network itself, without search, it can beat Keystone, like something like 10% gains. I checked again, I was really impressed. This is no search at all. It's just the network itself. You just take the maximum probability rules. It's deterministic, but it can beat Keystone. And it plays some really, I checked some capture rate, seminar. It played perfectly in that seminar. I was really surprised. Yeah. This is the soul, it's the power of neural network. Yeah. I hope to interest you and impress you by the power of neural network from my experience and also AlphaGo's success. I want to let you know very clearly that the neural network is really powerful. There's no doubt. We should. It will change. It has already changed many areas like speech recognition, like image recognition. Then, how do we train the battle network? We have the ILNet, so we need a data set because battle network basically just a regression over the outcome. You take a state, you take a board, right? You want to know what's the value of the ball evaluation. So we generate many games. We take one position on every game to prevent overfitting. There are totally 30 million games of self-play. So we generate 30 million games. Each game we take only one position randomly. Then because each game has outcome, right? Who wins the game, very clear. We just play to the end of the game. So we try basically to do regression over the state and outcome pairs. Okay, so minimize MSE, and the training time is still 1 week on 50 GPUs using Google Cloud. Now this is the plot of the error. We can see the value net power here. The top curve is the uniform random run. It means that if you run 100 playouts, it's completely uniform random. The loss is very large, right? Because this is a different move number. The x-axis is move number. And if you in the start, then it's not accurate. Right? It always thinks the game is even, of course. But the game has outcome, so it always 50%, 50. And you can see the value net is the solid line. It's just a bit higher than the bus network. What does that mean? That means that if you play the Monte Carlo playout directly by the network, every step you call network, which is very slow. But if you do that, the loss is actually not much lower than the battle net. So you can see actually battle net is like a cache of those positions outcome. You can treat it as a cache. But it's not, it doesn't remember, it's generalized, it's a power of generalization. Okay? So AlphaGo, basically the power of AlphaGo, it uses two neural networks, and then it combines the two neural networks into the search effectively. So we basically do a synchronized coding these neural networks, because they are really too slow. We cannot do synchronous. So now I think many people are familiar with Monte Carlo. I will go very fast. So basic selection, we just pick a move according to a value. It's action value plus some bonus term. The bonus term depends on the value returned by the policy network. So here, the policy network, its role is in the selection phase. Then when he reached the lead node, he do expansion. After the basic count is over a threshold. Then the key here is evaluation. Because when you reach the lead node, we do two kinds of evaluation. The first one is value network. The second one, we still do Monte Carlo rollouts. Then we try to mix these two values. Some people may be wondering why we don't just use value network if the value network is so powerful. So our experience found that actually the value network and the Monte Carlo rollouts, they are complementary. If you mix them, it's much stronger than each them standalone. Much stronger, it's like over 90%. So I try very hard to find out why. I try very hard to use just the value network, but it turned out that the mixing becomes much stronger. It's actually a bit like TD lambda. So basically you weight each different length of the different length of path, differently. So it actually, it's not exactly the same, but a bit like that. Yeah. So AlphaGo still use rollouts and use value network, but it mixes them. It's the source of power. When we do backup, so there are two kinds of backup. The Monte Carlo backup, basically synchronously, when you do a playout, you back propagation from the path, you go descend. But because value network is called asynchronously, when he finishes, he will asynchronously update the path when you descend in atomic. So whenever it's available, the searcher will use it. Okay, so all the details is in our Nature paper. Yeah, I would recommend you read it. It's a good paper, and we actually spend much time to make sure the details correct. But there's one detail is wrong. I can say here. And I'm sorry for that. That is the accuracy of raw policy. In the paper we write is 24%. It's actually, it should be 30%. Yeah. I noticed there's a researcher from another company. He said he cannot reproduce our result. But this is because I write the wrong number. Yeah, it should be 30%. Okay. Now we want to evaluate AlphaGo. Everybody know that in the AlphaGo big professional player, but at the time of Nature published, we actually very carefully to play different versions against different versions of program and self-play. So it's very surprising. At that time, AlphaGo beats almost every game against the program available. Hachi, Fuego, Zen, Very Strong. It only lost one game against Zen. Unluckily, yeah. I checked that game. Yeah, so we cannot. It's not.
Take the number. Take the legal.
Okay. Yeah. Okay. So this is in our Nature paper too. Now, after the Nature paper, we make another big jump. It's another 1,500 elo stronger AlphaGo since the Nature paper. Yeah. So this is roughly this is called V18. The V18 is actually much stronger than V13, which was playing against Fan Hui. Yeah, this is a big jump there, and we probably will publish another paper. We don't know, but we have some new ideas, and we do a lot of optimizations and stronger neural networks too. Yeah. But know that the elo rating are based on self-play. They are maybe biased because it's not. We cannot find other programs. Everything is 100%, so we cannot find other programs to test against. Yeah, okay. So we want to know how strong is AlphaGo. So we play against Fan Hui and Leiden. So we in March 2016 we beat Leiden 4-1. So we were actually before the match. I was a bit confident that we can beat them, but I was not sure. So my prediction was 3-2. 3 wins, 2 losses, yeah. But I was a bit confident, yeah, but because AlphaGo was improving very fast, a lot at that time. So it's a very, it's very nice result. I was very happy. The team was very happy too. Okay, now I will talk about many people. It's interesting. What happened in Game 4? Then you will see that in Game 4, AlphaGo was playing strangely, right? After the 78, this was move of God. Yeah, and then he triggered AlphaGo like into something crazy mode. Yeah. So we actually several months we spent much time to investigate why AlphaGo goes crazy. When I played the game, I was very surprised. What's going on? I know that AlphaGo is going to resign soon. Yeah, at that time. So we have two possible. We are not 100% sure, but we have two possible explanations. Which is the first one is probably the rising effect. That is, if you see the professional players their comments, the best variation they come up with is somehow a bit deep in the research. So it's probably the past network failed to guide the search up to that point. Yeah, that's possible. That's one possible explanation. The other one is probably the weakness of battle network. That is because these diagnose move 78 is like very, very low probability. So we know that battle network needs the self-play games to train, right? If the self-play games play very less that situation, then he will never see that situation. So when he into that situation, he will he just don't know how to, he just not familiar to it. Yeah. So that's possible that because that move was so low probability. Luckily, the latest version fixed the problem. Yeah. The latest version of AlphaGo we tried actually probably last week. Luckily, he played correctly, which means that if Leiden plays 78, the latest version of AlphaGo take over, AlphaGo might win the game. So we were happy with the fix. And then actually we didn't do much. Actually, we do machine learning. That the latest version automatically fix the problem. Yeah. Okay. If you have a question later, you can talk about the game for that. So what's next? AlphaGo is still improving. We are not closing AlphaGo now, but probably some other areas, right? The medical and robots, and yeah, there's many possibilities. Because DeepMind's mission is not just on Go. DeepMind's mission is to build AI, to solve AI, and to make the world a better place, to use AlphaGo's technique to other approaches, to solve more practical problems of human, that to make the world better. Yeah. So, of course, we are thinking the next step. Now, actually, we have a medical project now, as you might know. Okay, so this is the AlphaGo team. I'm very proud of working with them. This is every one of them contribute to AlphaGo, one side or the other. Yeah, it was really amazing. I can tell every member's contribution. Yeah, maybe someday we will write a book. Yeah. Every one of them was really helpful. Yeah, and it's a really nice experience of working with this team. Yeah, and it's really, they are nice people and they are very capable. They are very motivated. Yeah. So AlphaGo success depends on every one of them. Okay, thanks. I think this is my presentation.